Let us now consider the two-dimensional wave equation. Two-dimensional wave equation, it models vibrating membrane, for example. Let us consider the motion of a stretching elastic membrane, such as a drum head. This is a two-dimensional analog of a vibrating string problem. We will make the following assumption. The mass of the membrane per unit area is constant. It's an homogeneous membrane, and the membrane is perfectly flexible and offers no resistance to bending. We also assume that the membrane is stretched, like we see in this figure, and then fixed along its entire boundary in the XY plane. So this is the X direction and this is the Y direction. The tension per unit length, which we often called capital T, caused by the stretching the membrane, is the same at all points and in all direction, and does not change during motion. That's an important assumption. Moreover, we assume that the deflection of this membrane, which is the deflection in the Z direction, is during the motion is small compared to the size of the membrane. So that's also an important assumption. And all angles of inclination are small. So the boundary in this case is a circle. It can be a drum head, this membrane, but it's also possible to use other boundaries. It could be, for example, a square or a rectangle. Let us now show you some animations. If we have some initial displacement and then start the vibration, we can have something which is like this. So this is illustration of the vibration. Here is another illustration of another type of vibration where the initial deflection is different, or the initial velocity is different. Here is the case of a rectangular boundary. The membrane is stretched out to the surface of to the boundary and deflects like this. It can also be something like this. So in the next videos we are going to solve the two-dimensional wave equation, especially for the case of rectangles and circles.